Hello everyone, myself Dr. Kohli. So dear friends, we are discussing about the analytical chemistry chapter for FIBC chemistry syllabus, choice based credit system for the course CS202. Friends, in the previous lecture, we have discussed some of the important topics related to this chapter, that is calculation in analytical chemistry. So previously, what the topic we have discussed, like molarity, molality, then mole concept, numerical based on the mole concept. So these are the various important topics we have covered in the last videos. So in the today's lecture or video, we'll discuss some numerical based on the discussed topic previously. For example, here is a numerical that is we are going to discuss today. That is volume by how to calculate the weight to volume percentage, concentration in ppm, that is parts per million, as well as concentration in parts per billion, ppb. So these are the several types of solutions which can be prepared with the help of several techniques or formulas. For example, here is the first numerical. 250 ml of aqueous solution contains 45.1 milligram of pesticide. Give the concentration of pesticide in weight to volume percent, then ppm and ppb. So these are the three problems you have to solve. That is volume to weight, weight to volume percent, that is W by V, and ppm and ppb. So what is given in the formula or question? 250 ml aqueous solution is equal to 0.250 liter. So we have converted the ml to liter. 45.1 milligram of pesticide, that will be converted as 0.0451 gram, is equal to 45 into 1 into 10 raised to 3 microgram. So there are the conversion factors. So first, weight to volume percent, that is W by V. We have formula, weight of solute in gram divided by volume of solute in ml. Weight of solute is already given, that is the pesticide quantity. Then volume of solute in ml, so that is also given, 250 ml of aqueous solution. So that will be multiplied by the factor 100 percentage. So as the solution is prepared for the, it is a type of percent solution, so it is multiplied here by the 100%. So we'll add the quantities here. 0.451 gram divided by 250 ml into 100 percentage. The answer is 1.8 into 10 raised to 2%. So that amount will be required to prepare this solution, that is weight to volume percent solution. The second is concentration in ppm, that is parts per million, represented as a cppm. What is the formula to calculate that concentration in ppm? Mass of solute in milligram, so that is we have already converted in milligram or microgram. So already itself quantity is given in the milligram. So mass of solute milligram divided by volume of solute in liter. So mass of solute milligram is given 45.1 milligram pesticide, and that will be divided by 0.250 liter. So concentration in ppm will be equivalent to the 180 milligram per liter. So that is 180 ppm. So this much amount of solution concentration will be there for 45.1 milligram pesticide. The solution will be 180 ppm. Now concentration in ppb, that is called as a parts per billion. So again it has a formula, mass of solute in microgram. In case of ppm it was in milligram. So divided by volume of solution, we already converted the 45.1 milligram into microgram, multiplied by 10 raised to 3 to the power 3. So 45.1 into 10 raised to the power 3 microgram divided by 250 liter, that is volume of solvent, and the answer is 1.80 into 10 raised to 5 ppb, that is parts per billion. So there are the simple conversion formulas. With the help of that, we can calculate the concentration in parts per billion, concentration in parts per million, as well as the percent solution. So these are the formula. You have to remember these formulas. So weight of solute divided by gram divided by volume. So that will be the percent solution for weight by volume. And this is a ppm solution. Concentration in milligram, that is mass of solute in milligram divided by volume of solute, amount of volume. And for ppb, it is converted into the microgram quantity divided by volume of solute. That is the quantity. Now there are other types of concentration we are discussing here. There is a molar analytical concentration and molar equilibrium concentration. So what is the basic difference between these two? Molar analytical concentration is simply the molar concentration. So there is not too much difference between these two entities. The molar analytical concentration is the total number of moles of a solute without assuming the chemical state of solute in 1 liter of solution. So this is what the particular molar analytical concentration or molar analytical concentration or analytical concentration of a solution gives the total number of moles of a solute in 1 liter of solution. So that is simply the molar concentration actually. In case of molar equilibrium concentration, this is a slight variation in the molar equilibrium concentration and molar concentration. So what is the basic difference? In case of molar concentration, number of moles will be dissolved into the 1 liter of solution. The overall quantity is a molar concentration or molar analytical concentration, that is the same as molar quantity. In case of molar equilibrium concentration, so there is a basic difference between these two. So molar equilibrium concentration or equilibrium concentration is refers to the molar concentration of a particular species or solute in a solution at equilibrium state. So whenever the reaction approaches to the equilibrium, so what is its molar concentration of that species? What is the molar concentration of that species or solute at the equilibrium state? So that will be considered to prepare the molar equilibrium concentrations. So to specify the molar equilibrium concentration, it is very important to know how the solutes behaves upon the dissolution in solvent. So solvent, whenever the solute is dissolved into the solvent, so what is its behavior, like whether it is get completely dissolved, whether it is completely separated uh, into the ions. So this is the condition. For example, when HCl dissolve in water at equilibrium, their concentration will be 1 molar for each other. So H plus and Cl minus will be get separated, and complete dissolution of HCl into water will give the ions H plus and Cl minus, and for each the quantity of molarity will be 1 mole. So based on this discussion, we will have one problem. For example, calculate the molar analytical concentration and molar equilibrium concentration of solute in a aqueous solution. So we have to calculate both this quantity, that is molar concentration and molar equilibrium concentration. Now that solution, containing 250 milligram of trichloroacetic acid, which has a formula CCl3COH in 100 ml if the acid is a 73% ionized in water. So this is the formula. We have the trichloroacetic acid dissolved in 100 ml and its a dissociation is only 73%. So at equilibrium, its a dissociation is 73%. So trichloroacetic acid is dissociated as a CCl3CO minus plus H plus. So what is the main discussion here? It is a dissociated only 73% and remaining 27% is not a dissociated at equilibrium. So you have to calculate the molar equilibrium concentration according to this consideration. So here is the given quantities. Some mass of trichloroacetic acid uh, is given here. That is a CCl3COH 280 milligram, and that is converted into 280 into 10 raised to minus 3. So that is a 0.280 gram. So here is a some typo mistake. So volume of solution is 100 ml. So that is already given here, 100 ml volume solution. So that is again converted 100 into 10 raised to minus 3 liters. So that is a 0.1 liter quantity. 100 ml is equal to 0.1 liter. So we have converted this quantity into gram and liter. So similarly, the first thing we have to calculate is the number of moles for trichloroacetic acid. So number of moles will be indicated by small n. So what is the formula to calculate the number of moles? So that is a given mass of particular solute for which we have to calculate the number of moles in gram divided by the molar mass of that particular solute. So here the given mass is for the trichloroacetic acid. So we will consider the mass of trichloroacetic acid, that is given here 0.280 gram, and molar mass of that trichloroacetic acid, which is also given, that is 163.4 grams per mole. So whenever these two quantities are divided to each other, so that is 0.280 gram divided by 163.4 gram, the number of moles will be 0.017 mole. So number of moles we have calculated for trichloroacetic acid. The second thing, molar analytical concentration indicated by the capital M, number of moles of solute divided by volume of solution in liter. So that is a 0.017 moles we have calculated divided by 0.1 liter. So one digit here is a decrease by division of this factor. So 0.017 moles. This is the answer. That is a molar analytical concentration for that quantity will be 0.017 moles for 280 milligram. The molar quantity, that is a molar analytical concentration is 0.017 moles. Now second is what the thing important that in this particular solution, that is trichloroacetic acid in 100 ml of water, it is dissociated only 73%. So only 73% is dissociated. So probably H plus and CCl3CO minus, these are the ions formed in the solution. So at equilibrium concentration, CCl3COH is only 27% remaining. So thus CCl3 concentration, CCl3COH concentration is equal to molar concentration of trichloroacetic acid into percent dissociated divided by 100. By this formula, we will calculate the equilibrium concentration. So we already calculated the molar concentration for 280 milligram. So 0.017 mole into 27, that is undissociated, divided by 100 is equal to 0.17 mole into 0.27. So concentration of trichloroacetic acid is a 0.046 molar. So that is the equilibrium concentration. Second is the equilibrium concentration of H plus, as H plus ion is also dissociated at the equilibrium. So which is equivalent to the CCl3CO minus, and it's equivalent to the 73% of analytical concentration of trichloroacetic acid. So concentration of H plus is equal to concentration of this trichloroacetate and molar concentration of trichloroacetic acid into percent dissociated divided by 100. So the quantity will be multiplied by again molar concentration of trichloroacetic acid into 73 divided by 100. So it will be 0.012 mole. So by this way, we can calculate the molar equilibrium concentration at the equilibrium state. Now these are some important terms we have already seen in the previous lecture, that what is molarity and what is its symbol. So molarity is number of moles of solute divided by liter of solution, that is indicated by capital M. Molality, that concerned with the kg of solvent, that is number of moles dissolved in 1 kg of solvent, that is indicated by small m. And normality, that is the equivalent weight of solute dissolved in 1 liter, indicated by capital N. Weight percent solution, weight W by W, gram of solute divided by 100 gram of solution. Volume percent solution, gram of solute divided by 100 ml of solution, that is percent V by V. Weight to volume percent, that is W by V. We have already seen one example based on this. ppm, we also seen ppb, already discussed. Parts per thousand, that is ppt. These are some important analytical terms which are frequently used to prepare the different types of solution, and different molarity, molality and normality, as well as percent solution, ppm solution. So these all are very important terms. Now the very important topics from this same chapter, that is calculation in analytical chemistry, we will discuss as the significant figures. So what are actually the significant figures? So significant figures are also known as the significant digits. So precision or resolution, that are alternative names. So significant figures of a number in a positional notations are the digits in number that are reliable and absolutely necessary to indicate the quantity of something. So actually in every figure there are some significant figure, and there are some important points to be considered before assigning the significant digits or significant figures. So here there are some rules to assign the significant figures. So there are certain rules which we need to be followed to measure the significant figures of a calculated measurement. So these are some rules. For example, what is the first important point while assigning the significant digits or figures? First point is that the all non-zero digits are significant. So these are the numbers. So the whole numbers are actually the significant digits. So all non-zero, which are non-zero, that is from 1 to 9, all are significant. For example, 1, 2, 3, 4, 5. These are the 5 digits. So all 5 digits are significant digits. Second is the zeros between non-zero digits are significant. So suppose that this is the number 12012. So here is a zero in between these two digits. So what is the sentence here? Zeros between non-zero digits. So this is zero between two non-zero digits. So it will be significant. So here 5 significant figures or digits. Now the third rule is that trailing zero or final zero in the decimal portion only are significant. So trailing zero or final zero in the decimal portion. So is the decimal point where before this 20 are not significant. Whenever the digit started and after that the these are called as the trailing zeros or final zeros after decimal point. So there are three significant figures in this particular quantity of numbers, only three significant figures. So these are the important rules to be followed while calculating the significant figures. So following are the significant figure rules that are governed to the determination of significant figures. Those digits which are non-zero are significant. So we have already discussed this point. 6575. There are 4 significant figures, and in point 543 there are 3 significant figures. So after digit there are 3 whole numbers. So that's why there are 3 significant figures. If any zero precedes the non-zero digit, it is not significant. The preceding zero indicates the location of decimal point. For example, in 0.005 there is only 1, and in the number 0.0232 has 3 figures. So this is called as a preceding zero. If zero preceding the non-zero digit, so here after this 20 there is a digit. Okay, so before that these 2 figures are not significant. So here only one significant figure, that is 5. Afterwards you see the number 0.00232. So these are the preceding zero. After that these are the 3 digits 232, and hence it has only 3 significant figures. So that is 232, 3 significant figures. If there is a zero between two non-zero digits, then it is also a significant figure. So see here, for example, 5006. So 0 is coming in between the two non-zero digits. So all will be considered as significant figures, and this is separate significant figure, that is a whole number 4. So 1, 2, 3, 4, that is 50064 plus this 4, 1. So that is total 5 significant figures are there. So if there is a 0.0, then that will be not considered as a significant figure. But here is a whole number and these are the 4 digits. So overall the 5 significant figure will be considered. Zeros at the end or on the right side of the number are also significant. So here is the example 500 as a 3 significant figures. So you can see the significant figure example here. We already discussed 4 significant figures. So 2 plus 2, 4. 1, 2, 3, 4, 5. So here is the digits is coming before the 0. So only 2 significant figures. Here digit, then decimal point after 0. So 3 significant figures. So here also 0 is coming before this 5. And 5 and the last digit after, so last 0 after the digit 5 will be considered as a significant figure. So here 3 significant figures are there. So you can see how many significant figures. So you see the table and you can calculate the significant figures from this table for your reference. And then rounding off is another point. So that is, for example, how to round off the significant figures. So here you see these are the 2 digits. So see the third digit, and if the after that third digit the fourth digit is more than 5, then it will be rounded as a by adding 1 to this 3 digit, that is 884. So if this fourth digit is less than 5, for example, if this fourth digit will be 2 or 1 instead of 6, so it will be not rounded off. So it will be rounded off as 883, not as 884. So this is the rule of rounding off. So you see the fourth figure here, this digit is not greater than 5. So 3 digits will be considered as a 783 only. If this fourth digit was, suppose that it was 9, then it will be added to this 3 as 1. So the overall quantity would be 8784. So rounding off rules are there. So see the 4 digit, and if the fourth digit is greater than 5, so it will be rounded at to the left side digit as a +1. So that is 884. So these are the several rules for rounding off, and these are the some important topics we have discussed in the today's lecture. I hope that this lecture would be definitely helpful for you to solve several problems regarding the exam. And these were the some important topics we have discussed in the today's lecture. So significant figures, rounding off. So these all are the topics. So thank you very much for watching. Thank you very much for watching this video.